In this video, we are going to look at section 1.2, which is covering fractions. A fraction is a number we need for measuring. For counting, we have the natural numbers, 1, 2, 3, 4. But when we measure something, such as length, it will not always be a whole number. Therefore, we need numbers that are less than 1, numbers that are parts of 1. Half of 1, a third, a fourth, a fifth, a millionth. So some terminology we need as we begin. The numerator is a top quantity in a fraction. The denominator is the bottom quantity of a fraction. And to help you remember this, you can think that D for denominator, D for down. So the denominator is the down or the bottom number in the fraction. A proper fraction is one where the numerator is less than the denominator. So the top number is smaller than the bottom number. Note, a proper fraction does not convert to any other type of fraction. But an improper fraction is one where the numerator is larger than or equal to the denominator. And a mixed number is a natural number with a proper fraction part. There are times when improper fractions must be converted to mixed numbers or vice versa. So converting a mixed number to an improper fraction, first we multiply the denominator of the fraction by the natural number and then add the numerator to this product. And then second, we place the result from step 1 over the denominator of the original mixed number. So let's take a look at some examples. Example 1, convert each of the following mixed numbers to improper fractions. So our first example is 5 3/7. For this example, 5 is the whole number, and it's also called a natural number. 3 will be our numerator, and 7 will be the denominator. So for step 1, we're going to take that denominator, 7, and we're going to multiply it by 5. And then we're going to add the numerator of 3 to that product. The product means just the answer to a multiplication problem. And then we're going to put that result over the original denominator in our mixed number, which is 7. 7 times 5 is 35. Plus 3 more will give us 38. So our result is 38 over 7. So what this means is 5 3/7 is equal to 38/7. Let's try another one. For B, we have 16 1/5. So let's take our 5 and multiply it by 16 and then add 1. And all of that will be over our denominator of 5. And so 5 times 16 will equal 80. 80 plus 1 will give us 81. So 16 1/5 equals 81/5. And another example, we have 20 3/4. And so for this one, I'm going to show you what I do for myself when I'm changing a mixed number to an improper fraction. I draw a loop starting with my denominator, my 4, going around the natural number 20 and pointing to the numerator, which is a 3. And then I add to it a times sign in between the 4 and the 20, and a plus sign between the 20 and the 3. So I'm going around starting from the 4, doing 4 times 20 plus 3. It's just a visual reminder for me of the steps involved in changing a mixed number to an improper fraction. So again, that illustration shows 4 times 20, which gives us 80, plus 3 more, which gives us 83. And we're always keeping the denominator of our original number, and the denominator here is 4. And so 20 3/4 is equal to 83/4. Now let's look at doing the opposite. Let's try converting an improper fraction into a mixed number. This also has 2 steps. First, we're going to divide the numerator into divide the denominator into the numerator, and then record the quotient, which is the answer of a division problem, and the remainder, what's left over. And then we're going to write the mixed number using the following form. Our quotient is going to be our natural part number, our whole number, and then our fractional part will have the remainder as the top or numerator, and the original denominator from the improper fraction as the denominator. So just as before, the denominator will stay the same. So let's look at a couple examples for this as well. For example 2, we're going to convert each of the following improper fractions into mixed numbers. So again, improper fraction is when the top number is the same as or larger than the bottom number. So it's top heavy. And to do this, our first step is to divide. So we need to figure out how many times 7 can go into 17. And the way you set this up using long division is, remember, D for denominator, D for down, and the other way you can think of it is down and out. Our long division symbol looks like that. And our D down number, 7, goes on the out side of the long division symbol, so down and out. So we're going to divide 7 into 17. So our numerator goes inside the division sign, and then we're going to divide. How many times can 7 go into 17? Well, if we think 7 times 1 is obviously 7, 7 times 2 is 14, 7 times 3 is 21. So that's a little bit too much. So it can only go in 2 times. And then 2 times the 7, as we just mentioned, is 14. So when we take 14 away, which represents the 2 whole that we have here, we get a remainder of 3. So 2 remainder 3 is written as 2 as a whole number. Our remainder 3 is our numerator, and then our original denominator was 7. So 17/7 is equal to 2 3/7. Let's try the second one. We have 13/9. So again, down and out, the 9 is going to be the number that goes on the outside of our division bar, and 13 goes on the inside. And we know 9 times 1 is 9. If we go to 9 times 2, that's 18. So we're already at too much. So it can only go in 1 time. So 1 times 9 is 9. So let's take 9 away from 13 and see what we have left over. We have 4 left over. So 1 remainder 4 is the same as 1 with 4 as our numerator. And then again, we look and see that we had 9 as a denominator. So that stays the same. So 13/9 is equal to 1 4/9. And let's look at C. 19 is our denominator and 83 is our numerator. So let's put 19 on the outside, down and out, and then 83 on the inside. And I don't know my multiples of 19. I'm guessing you don't either. So let's look at this using numbers that we can think of easily. 19 is really close to 20. So if we count by 20s, 20, 40, 60, 80, 80 is the closest that we're going to get to 83, which is 20 times 4. So I'm betting that 19 can only go into 83 4 times as well. So let's check that. We can always erase and change our answer if it doesn't work. But let's try 4 times. And then 4 times 19, the calculator tells me that that's 76. And so when I subtract 76 from 83, I get 7 left over. 7 is smaller than 19, so I know that I didn't make too small of a number. If I would have tried 3 and done that, my remainder would be larger than 19, which means I could have gotten more 19s out of them. But in this case, we didn't, so we're good. And so 4 and 7/19 is our answer because we got 4 remainder 7 when we divided. Fractions can be simplified by first factoring the natural numbers that make up the numerator and the denominator. To factor a natural number means to write it as 2 or more natural numbers being multiplied. For example, 21 can be factored as 7 times 3, which are called factors, and 21 is the product. So notice the example. 7 is a factor of 21, and 3 is a factor of 21, and the product of 7 and 3 is 21. So looking at factors or breaking a number down into smaller parts that multiply to get the answer will help us with simplifying some fractions. Are 7 and 3 the only factors of 21? The answer is no, since 21 can also be factored as 1 times 21. Thus, 1 and 21 are also factors of 21. Some natural numbers only have 2 factors, the number itself and 1. These are called prime numbers. A prime number is a natural number greater than 1 that only has itself and 1 as factors. So examples are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and so on. So for any of those numbers listed there, 1 times the number itself is the only 2 numbers that can divide evenly into that. So 13 can only be broken down to 13 times 1. So that is considered a prime number. Note that the number 1 is not a prime number because if we look at the definition, it says that it has only itself and 1 as factors. So it has exactly 2 factors. And the only way we can get 1 is 1 times 1, and which is only 1 factor. So the number 1 is in a category all by itself. A composite number, on the other hand, is a natural number greater than 1 that is not a prime number. So that means that every composite number can be expressed as a product of prime numbers. And so we saw 21 as an example. That would be considered a composite number because not only can we do 1 times 21 to get 21 as an answer, but we can also do 7 times 3 to get 21. And notice that 7 and 3 are both prime numbers. So what we're going to do now is to find the prime factorization of some numbers. Prime factorization means to create a number where we're using the product, remember the multiplication, of only those prime numbers. So we're breaking a number down into a multiplication problem that is using all prime numbers that would give you the number that we were given as the answer. And there's many different ways that you can break them down. And so let's look at our first example of 100. You might look at 100 and think that it is automatically 10 times 10. That's an easy multiplication fact to remember. But 10 is not a prime number, so we would have to continue to factor it. And usually prime factorization is shown using a factor tree where you're taking the number and just branching off from its multiplication facts. So as I mentioned, 100 can be written as 10 times 10. And notice 10 is an even number. Any even number can be divided by 2. And so 10 can be broken down as well as 2 times 5. 2 is a prime number, so we can't break that number down any farther, and so is 5. But we need to break down the other 10 into 2 and 5 as well. So the numbers that I circled are the end of the branches, and they're all prime numbers. We can't go any further with those. And notice we have 2 times 5 times 2 times 5. We can rearrange them to group them together and say that we have 2 times 2 times 5 times 5. And again, I apologize for my messy writing. I'm trying to use the mouse pad to write. But notice we have 2 2s and 2 5s. We can simplify writing that, making it easier to write by using exponents to show repeated multiplication. So when we write a number using an exponent, the base, the large number that we write, is going to be the number that we see. The exponent tells us how many times that number is getting multiplied together. So we have 2's that we see, and we have 2 of them. And same with the 5's. We see a 5, and we see 2 of them. So 100 can be written as 2 to the second power times 5 to the second power, which means 2 times 2 times 5 times 5. And if we look at that, 2 times 2 equals 4. And we'll take our 4 times 5, which equals 20. And then the 20 times 5 gives us 100. And that is useful in simplifying fractions, and we'll see that in just a little bit. But what I want to show you now with 100 is that there is more than one way that you can break down a prime number often. And now if it's just like 21 with 7 times 3, those are the only 2 numbers you can get. But let's take our 100 again. I mentioned that any even number can be divisible by 2, so what if we started off dividing by 2? Well, half of 2 would be 50, so 2 times 50 is 100. And 2 is a prime number, so it stops. So that branch is done. But 50 is a composite number as well, and it's still even, it ends in a 0, so we can still divide by 2. And half of 50 would be 25. And again, our 2 is prime, but our 25 is not, so we need to break down 25. And since 25 ends in a 5, I know it can be divisible by 5, and 25 is 5 times 5. And those are both prime numbers. So notice my factor tree looks different than my first one, but I still have 2 times 2 times 5 times 5. At the end, the prime factorization will be the same, no matter how you decide to break up the number to start with. So let's take a look at 525 now. 525 can be broken down a couple different ways, again, but when I see it, I'm not sure other than 5 what works. It ends in 5, so I'm going to start with 5. So to help me, I put 525 divided by 5 in my calculator, and I got that it goes in 105 times. So 105 times 5 is 525. So now I need to take my 105 and continue breaking it down. So again, since it ends in 5, I said that one of the factors has to be 5, which is prime. And then 105 divided by 5 is 21. And 21, we've already seen in this lesson, it is the product of 3 times 7, which are prime numbers. So we have 5 times 5 times 3 times 7. And if we multiplied all 4 of those numbers together, we would get 525. And so let's write it going from smallest number to largest number, and then using our exponents to show the repeated 5s to make it easier. So 525 is 3 times 7 times 5. But since we have 2 5s, we'll put the second power on the 5 to show that there is 2. So 3 times 7 times 5 to the second power, which is also called squared. So 3 times 7 times 5 squared, all multiplied together will give you 525. So now let's look at our last example, 520. So you could look at this, and since it ends in 0, know that it can be divided by 10. So you can do 10 times 52 and break it that way. But again, I like to do 5 with this one because I know since it ends in a 0, it is divisible by 5 as well. And so if I divide this by 5, we will get 104. Notice since it ends in 0, it's also even, so you could have started dividing by 2. That would work, but let's use 2 now. And if we take 104 and divide it in half, or divide by 2, we will get 52. And 52 is even, so let's divide 52 by 2. And we'll get 26. And then 26 is even again, so let's keep dividing by 2. And half of 26 is 13. Now 13 is a prime number, but if it's a number you're not sure if it's prime or not, you can try playing around with it in your calculator and do 13. We know it's not going to be divisible by 2 because it's not an even number, but you can try dividing it by 3 maybe, or 7, or things like that, just to make sure, if you're not sure, it's a prime number, that it is 1. And so notice here we have 5 times 2 times 2 times another 2 times 13. So if we write that using our exponent again to help us, and from smallest number to largest number, we have a 2 that's being used 3 times, so 2 to the 3rd power, which is also referred to as 2 cubed, but 2 to the 3rd power. Then we have 1, 5, so we don't need an exponent there, and we have a 13. So 2 times 2 times 2, or 2 to the 3rd power, times 5 times 13. If we enter that in the calculator to double check, we should get 520 as an answer. Two fractions are equivalent if they represent the same value. Writing a fraction as an equivalent fraction with a smaller denominator is called reducing a fraction. A fraction is reduced to its lowest terms when the numerator and the denominator have no common factors other than 1. So the example that they give us, just kind of a pattern, if the top can be written as A times C and the bottom can be written as B times C, notice C is a common factor that can cancel each other out, and we're left with A over B as a reduced fraction, but C cannot be 0 because we don't have the ability to put 0 in the bottom of a fraction, because if you think about it as dividing, we can't divide anything by 0. We can have nothing to divide into, but we can't divide by 0. So there's never going to be any zeros in the bottom of your fractions. So what this means, as I just mentioned, is that any fraction we can write as a product of numbers where the numerator and the denominator both have a common factor, a quantity that is multiplied by another. Then we can reduce the fraction by dividing both the numerator and the denominator by that common factor. So note, reducing and rewriting mixed numbers are not the same things. Fractions must be reduced in every problem. So what this is saying is taking an improper fraction and writing it as a mixed number isn't always going to give you a fraction that's in simplest form. And so you have to make sure that your fractions are as low as possible. And so if we look at reducing the following fractions to its lowest term, one thing that can help us is using our prime factorization. And so 6 is the product of 2 times 3. That's the only way we can write 6 besides 1 times 6. And 14 is even, so it's 2, but that's times 7. So notice there's a 2 in the numerator and a 2 in the denominator. If we look at those two together, it's like writing 1, because anything divided by itself is 1, or 2 over 2 would equal 1. So we're really just taking away a value of 1, and notice what we have left over. What we have left over is our reduced fraction, which is 3/7. Now, if we were to do our prime factorization of 15, that one, we only have 2 factors other than 1 and 15, which is 3 times 5. If we want to do the prime factorization of 75, we can do that. So if we take 75 and break it down, since it is ending in 5, we know we can divide by 5. And if we do that, 75 divided by 5 gives us 15. So 5 is prime. And 15 can be divided by 5 as well. And it's 5 times 3. So 75 is 5 times 5 times 3. And here, to be able to reduce, we don't want to write it using exponents. So we'll say that we have a 3, because we're going to put it smallest to biggest, times 5 times 5. So look what happens. We have a 3 that can cancel out with a 3 on the bottom. We also have a 5 on the top that can cancel out with a 5 on the bottom. And then there's nothing else to be able to pair top to bottom, so we're finished. But look what happened when we reduced. We canceled out both the 3 and the 5, which means 15 can divide evenly into 75. And whenever you do that, remember that anything times 1 stays the same. So really we have, I would think of it as invisible. There's an invisible 1 there to help. So when everything is canceled out in a problem, you're going to have 1 left in that spot. And then notice the 3 and the 5 here are canceled, and all we have left is a single 5 there. So 15 over 75 reduces down to 1/5. Let's look at 25 over 11. 25, we know, is the product of 5 times 5. 11 is a prime number. The only way we can write that is 1 times 11. Notice there is nothing in common. We can't cancel anything out. So our answer cannot be simplified. We have our 5 times 5, which was the 25, and 1 times 11, which is 11. So 25 over 11 cannot be simplified. You could write it as a mixed number, and 11 goes into 25 2 times, which is 22. So that gives us 3 left over. But that's not necessary. We can leave it as an improper fraction. 32 over 80 is our next example. So if we break down 32, it's even, so we can divide by 2, which again is prime. 2 goes into 32 16 times. 16 is also even, and I'm going to put the 2 this side because I'm running out of room on my right. So 16 is 2 times 8. 8 is even again, so 8 is 2 times 4. So that 2 is prime, and then 4 breaks down to 2 times 2. So 32 is a product of all these 2's together. There's 1, 2, 3, 4, 5. So again, I don't want to write it as 2 to the 5th power because I'm going to be able to cancel a 1-to-1 ratio between the top and the bottom. Oh, it's getting messy. That looks kind of like a fancy 1. There we go. And 80 can be broken down as well. And I'm not going to show you the factor tree just to save some time, but if you want to pause the video and do the factor tree for 80 as practice, you can pause it and then continue on. 80 breaks down to 2 times 2 times 2 times 2 times 5. So let's see what we can cancel out. 1, 2 on the top cancels 1, 2 on the bottom. Here's a second 2 on the top with a second 2 on the bottom, another 2, and even another 2. So everything cancels but 1 on the top, which is 2, and 1 on the bottom, which is 5. So 32 over 80 is the same as 2 over 5. Now let's look at 63 over 93. 63 is the same as 9 times 7, and then that 9 can be broken down to 3 times 3. So 63 is 3 times 3 times 7. If we divide 93 by 3, we get 31 as an answer. And 31 is actually a prime number. We could check different things and they're not going to work. If we try dividing it in the calculator, we're going to get this long decimal instead of a whole number. So that shows us that nothing else can divide into it. So all we can divide from the top and the bottom or cancel out is a single 3. Notice on the top we have a 3 and a 7. So that's not 37, it's 3 times 7, which is 21. And then we have our 31 on the bottom. So 63 over 93 is the same as 21 over 31. And let's look at F. We have 125 over 50. So we've been using prime factorization, but let's kind of change things up a little bit for this one. Because when I see numbers like this, I think of money and quarters. So if I look at the top, I think of it as $1.25, and there's 5 quarters and $1.25. So I'm going to say this is 5 times 25. And then 50 is the same as 2 quarters. 50 cents is 2.25 cents. So notice, instead of breaking it down all the way that I could have written this 25 as 5 times 5 and this 25 as 5 times 5. I just left them as 25s because I can still cancel a 25 from the top and a 25 from the bottom. And I'm left with 5 over 2, 5 halves, or we can write that as 2 1/2. So there's other ways that you can do it besides just using prime factorization. If you are used to and comfortable just dividing things out without breaking it as small as they can, that's fine. But try and make sure that you show some work, because remember, on a quiz or test, you have to show your work. And if something goes wrong and you only wrote the answer, then I don't have anything to be able to give you any credit for. Whereas if you show some work and maybe you just made a small mistake in factoring out the denominator, but you did everything in the numerator right and you canceled some stuff out right, or maybe you wrote down a 2 and then when you looked back at it you saw a 1, like with my crazy looking 2, then I'll be able to see that you knew what you were doing, you just made a small mistake, and then I would at least be able to give you partial credit for that answer. So now it's time for you to do the practice problems in section 1.2, and these are on page 16 and 17 in your workbook. If you have any questions, don't hesitate to send me an email. Otherwise, I'll see you next time.